Dope, okay.
Should we start off with introductions?
Yes.
All right, this is Evan Forbes, and he works at Celestia as the protocol lead.
This is Callum. Callum's a core dev. We work on the same team.
You're working on the same team.
And today we're going to talk about based rollups, fork choice rules, and like really dive into them. And I think the first good place to start is actually talking about the problems that they're solving. And there's two sort of distinct problems that sometimes they solve both at the same time, sometimes they don't. And that can maybe lead to some issues. And then after we talk about the problems that they're trying to solve, then Callum can talk about the transaction flow of and the different roles involved. And then we can talk about MEV and fork choice and stuff. OK, so the problems that we're trying to solve are twofold. The first is the simplest, is a decentralized sequencer set for a validator, or for a rollup. For a rollup, you don't want to have like a centralized sequencer. And because that's bad, because now you have a centralized sequencer. Simultaneously, you're a rollup. You don't want to have your own sequencer set either, because that defeats the purpose of using a rollup. I would rather just spin up a Cosmos chain. That's easier. So if I want something that actually gets the benefits of these things, you can use something called a base rollup. And a base rollup has, in my opinion, one distinct property. And that is that it simply executes transactions after you reach consensus. So first, you have some sort of ordering of the transactions. So if this is Celestia, this is the Celestia square. We're going to stick some transactions in here for my namespace. That's my base rollup. We're going to pull this down. And after we reach consensus on it, after we timestamp it, after we publish it, now we have the transactions, and now we execute them. So now we have, however you execute your transactions, and this can be entirely arbitrary to your chain. You execute. And then you're a rollup, so now you're doing some proving as well. But we'll actually talk about proving later. That is the sole purpose of a base rollup, the only thing that you need. And the thing here is that since you're executing your transactions after the fact, you can actually share the sequencing across many different nodes because they don't need to know anything about you. They literally just order the data and stick it in one place. And as we know, that's actually scalable because it's separate. They are not paying attention to anything to do with your state machine. They don't care. They don't care about your ordering. They don't care about anything. And because of that, it's actually scalable. The second problem that we're trying to solve is MEV. So the classic case is with a liquidation. Someone has a loan, and it gets liquidated. So they have collateral up for that loan. And someone needs to bid for that collateral. So they have, the original loan is worth 100, I'm just going to call it T for tokens. So you have 100 of these tokens. That was the original collateral for the loan. Now, whatever the value in this liquidation, now they deemed that you're underwater or getting close to being underwater, which means that the value here, the collateral, is not enough to back up your loan. So we're going to liquidate you. We're going to sell your collateral while it's still worth enough to cover your loan payment so that we can actually keep the system, maintain that the system is good. So to do that, we're going to have a discount. So we're going to sell your 100 tokens. We're going to list it at, if this is denominated in some other currency, let's just call the other currency A. We're going to assume that originally it was 1-to-1, but now the price of your collateral went down. So the price of T went down. Now you have 70A. Anyone that pays 70A is going to get your 100T. Okay? So that's there. But now we actually want something better than that. That kind of sucks because the price is somewhere between 70 and something else. But when we actually liquidate your collateral, usually we have a bidding system. We want whoever is willing to bid to find the correct price. This is the entire purpose of auctions, right? We try to find a correct price. When we do this, in theory, it sounds nice. I have an auction. I'm going to bid up here to whatever the actual price is. Let's say the actual price is here. And as a user, it sucks. I get liquidated. I lose this amount. But really, I'm getting like 90 out of my 100. It's not that bad of a cut. But when you add MEV in here, now it assumes that the auction is actually credible. It assumes that the auction can actually make these comparisons in a reliable way, but it can't. Because the proposer is the one who gets to determine what is the input into that auction. The proposer determines, the proposer has monopoly over what goes in. So what does the proposer do? The proposer says, oh, I'm going to have people bid. I'm still going to have an auction. But it's an auction to pay who pays me the most for this bid. So they end up, what happens, this happens, is that this money right here, all of this extra behind this discount, that goes to the proposer. It doesn't go back to the user. The proposer captures all that value for doing what? Just simply having a monopoly, not actually producing any value, not actually doing anything. Yeah?
So you're saying that like proposers are doing this right now, like this is in their software, like live?
This happens like every 12 seconds on Ethereum right now. Yeah. So this is really bad. We want to find something like this to either direct this value back to the user, so to have a credible auction, or we want to find a way to capture the profits of the system in a more programmatic way. So we're going to choose the winners. We're going to choose, instead of going to the proposer, we're going to go to someone else. So that was a bit of an elaborate illustration or ramble, but those are the two problems that we're trying to solve here.
Like you're essentially talking about value capture. Can the app do that, or will that be taken by external parties?
Yeah.
That's one of them. And the second thing is going back to the whole, like, where do you get your inclusion and ordering guarantees from?
Yeah, yeah.
Okay.
So the decentralized sequencer set, the sequencer is publishing and timestamping your transactions. And because they do that, now you're able to have a decentralized sequencer set while not having to get your own sequencer set, right? So that's what based rollups are solving. They solve this, this ability to have a decentralized sequencer set in a permissionless way. I don't have to ask anyone. I just write some transaction. I write my state machine, and then users just start using it.
Yeah.
And that's it.
Because if we were to rewind or like unwind a little bit,
yeah.
The whole like goal of this as a whole was verifiable execution. That's what Ethereum tried to do. Ethereum didn't scale, so we tried to find an alternative solution to scale. Here came Celestia. Then how Celestia, when it was doing is, instead of having 100 nodes doing, well, however big the sort of network is, instead of having all of them do both consensus and execution, we're going to have the 100 do just the consensus, because the execution is the computationally intense part, and have each individual application, maybe it's only a couple of nodes, do the execution itself. So we're trying to like outsource the execution, and then these have now been named rollups, right? So this is kind of straightforward, but just to get there. Now what do we see in our current rollups? We see that there are often these like centralized sequences. So now you've got these problems about censorship resistance. Like now you're posting your data to Celestia, but you're using some sort of sequencer, and they have control of the order. And so we're trying, like I think what you're trying to get around here is how do we like avoid these things, because then now you're relying on that sequencer for some censorship resistance, and now, now that sequencer can also extract MEV. And so base is what you're presenting as like the solution to this, where like it avoids these.
Yeah, we get two birds stoned at once.
All right, continue.
So now we can go through like the transaction flow. What does this actually look like in real life, and what are the roles of the things?
Yeah. So I think one of the like confusing parts, if we're going with this like modular thesis, which is kind of very similar to like the microservices architecture in Web 2 like a decade ago, what do these different categories look like? And I think there's a lot of debate about where they like lie, and I think we're still trying to like fine tune what they look like. I guess one of them we have is this like DA layer, and it kind of depends how you use it. So for example, with Celestia, there's like three things that Celestia is providing. It's providing inclusion, so proof of something inclusion. I can call this order. So what is the order of these things? And this is done by consensus anyway, so any like Cosmos SDK chain, for what it's worth, does these things. The thing that Celestia does on top is a way of sampling this stuff. So this is how you have your data available guarantees. And this is the whole like scaling solution where instead of downloading all that data that has been included, you can have a more efficient way of doing this. Now, that's the sort of like DA layer side of these things. We have this emerging sequencing layer. So the like of Astria. And Astria has to be decentralized because you're trusting Astria to do order for you, right? So now instead of relying on Celestia for ordering, you're using Astria. And Astria can do this a lot faster, so it means you get your ordering a bit sooner. So you now, if you wanted to as your rollup, start using Astria, so you'd be publishing transactions to Astria. That'd be sort of almost like a DA, batching them together, and then you can know ahead of time what's in those transactions, and then they eventually go into Celestia. But the problem with something like Astria is that now they dictate order, so you're now dependent on them for sort of like either censoring you or sort of like sandwiching you. Like now they can extract that MEV. And so the whole point of like the base layer is like, let's not rely on both of these two things. So now you're relying on the validator set of the sequencing layer and the validator set of the DA layer. The DA layer is already doing ordering for you. You kind of get that. So why are you paying extra for the sequencing itself? Can we just have some system where you post stuff directly to the DA layer? Do you want to jump in?
One important note is that like based rollups can be used with either. And what Callum is saying is that you don't have to use a sequencing layer. You could use the DA layer for the sequencing layer at the same time. The problem with base rollups is that you inherit that sequencing from the base layer. So if your base layer has slow sequencing, well, now you have slow sequencing as well. So the reason for having a separate sequencing layer, still a base rollup either way, in my opinion. Like a base rollup doesn't, like the whole, it's only champagne if it's from some region of France, right, thing?
Champagne.
Yeah, from the Champagne.
That's the region.
Yes. Thank you, thank you. It's like a base rollup is not just a base rollup because it's on an L1. A base rollup is a base rollup because it has deferred execution and can share a sequencer set. Yeah. So the thing that you're getting here from the sequencing layer is you're getting these short-term commitments. I think one of the fun things, I don't know, I don't want to go on too big of a tangent, but the 4 things that Sriram always mentions for like the security of a chain, it's like you have DA, you have censorship resistance, you have reorg resistance. I'm not even going to write this out. And then there's one more. What is it? I need to go look at the tweet. But anyway, you can get all 3 of these. Or in this case, if the sequencing layer is posting its blocks to the DA layer, eventually you get all 3 of these from the DA layer. Mm-hmm. But the sequencing layer, its sole purpose, in this case, is to give you these things for 12 seconds.
Yeah. And if you saw the talk about on fast block slow squares, the idea is that if the DA layer can do this faster, so at a like per second time, then actually you don't really need a sequencing layer. You don't actually need that added like level of security. What you can have is maybe an aggregation layer, so something, I actually don't want to use the word aggregation layer because it has already some sort of context, but some sort of batching, right? So you can always post directly to Celestia. That way you're relying on Celestia for censorship resistance. You're not relying on them. They're not it's sort of permissionless. But if you want to get things cheaper, so you don't have to pay for the entire signature stuff on Celestia, you can sort of batch them through some sort of batch provider. And this is like some sort of permissionless system. You might imagine there might be 3 or 4 competing to have the lowest price, batching it there. And if, for example, this guy is trying to censor your transaction, you just submit it directly to the DA layer. Okay, so that was like the first part of it. And then should we talk about like execution improving now?
Yeah.
Okay, so this is the sort of like the one aspect. So it's just getting this sort of data on chain. Now the second part is like, how do we work around execution improving? And so, like one of the things that works quite well with Celestia is like a proven network. So you would just have the flow is once the sort of transactions are on Celestia, there'd be some way where you like provers would a prover would realize there's enough of like, we're not really going to get into payments, but sort of like incentive for them to now produce a proof. So there'd be enough transactions there. They would then execute, find out the new state route, and then create a proof for that. And then that proof would then go into the DA layer. And so then you as your light client, for this like base rollup, the way that you're working is you're reading Celestia for proof that your data is included, proof that the block is published in terms of the sampling, and then also now the proof from the like execution itself. Do you want to add something into that?
No.
Okay, so how do we explain this to you in a very like simpler way?
Maybe like pretend I'm a user.
Yeah.
I'm going to sign something.
And who are the other agents, right?
Yeah, let's follow it.
So there's like one
let's draw it
flow
out.
where you can submit to this person who batches things together.
Wait.
And then
let's draw it out. Let's get a. All right. I signed a transaction. Here you go.
Who am I?
We'll follow it. So transaction. It's signed. It's
So
from me.
the batching thing is optional. You kind of don't need it here. And so I think maybe for a simpler method, you could just say you submit it to the DA
That's
layer.
a good idea.
So you submit it to the DA layer, and then you basically have people from all over the network submitting their transactions. Then you'll have some sort of like roll-up node. And the whole idea is like instead of having this like network, it's permissioned. So you can have multiple roll-up nodes. You're drawing the square?
Yeah.
So you'll have someone who's like incentivized to run a roll-up node because they get the rewards for producing proofs, right? And so they will read off the transactions, and the transactions will sort of say some sort of fee towards that prover. Once there is a certain amount, they will then execute those transactions belonging to that namespace, and then produce the proof, and then submit the proof back into the DA layer. And so then you, as the user, you submit your transaction, you sample the square that it's available and that your transaction is included, and then you sample then you sort of like retrieve the proof, you verify the proof of the state, now you know the new updated state that your transaction went through. Does that make sense? Do we have any questions just to like stop it here? Yeah?
Maybe is there a concise way to say what exactly is the difference between a based rollup and a non-based rollup? Like what's the unique feature that a based rollup has to have?
In my view, it's like debated. I think the base term is like all over the place, but I will let you take the...
I think the sole technical thing that you need is deferred execution. So I execute the transactions only after they have consensus. So that's it. And anything that has that could be a based rollup because now the consensus is external, right? Everything I'm like drawing a line in the sand and saying I'm only handling things on this side. Therefore, everything on that side can be arbitrary, can be a different chain even, right?
Okay, so deferred execution. We're saying that it might be a based rollup, and so what?
No. That's my definition of a based rollup, and I'm quite opinionated on that.
Yeah, that's why I said that it's like kind of
yeah,
debated.
I know. Some people say base rollups are only base rollups if they're on like the L1. So like Ethereum doesn't refer to base rollups if it uses a shared sequencer. It's not a base rollup. It's only a base rollup if it's on the L1. I think that's a silly definition. It's not useful.
Yeah. I'm not sort of worried about the nomenclature. I think the important part for me is saying that like the DA layer gives you a lot more than what people are going to be using it for. Like a lot of people don't have, okay, so you've seen this rise of like sequencing layers. And so my like pushback about this is like, do we actually really like, okay, great, we've got this modular thesis, but are we adding modules just for the sake of it? Or are we adding different layers for the sake of it? Like what are they actually like inherently providing? And I think if you actually dig a little bit deeper, all they're doing is making now, instead of relying just on the security of the validator set of the DA layer, now you're relying on the validator set of or like the censorship resistance of the sequencing layer. So you're increasing the amount of things that you're relying on. And so if you can kind of reduce that, and like if you're a rollup, you're always going to have to be, if it's Ethereum or Celestia or anything like that, you're always going to have to be reliant on that validator set. So you can't eliminate it beyond that. But I think instead of just adding like modules just for the sake of it, I think we should be really like critical about how many, like what is that additional change to the security.
Okay.
And so I think in many cases you don't need decentralized systems. You kind of need like create open market systems. So where people, and so I made this use case about aggregators. So they're like competing with one another to make the like cheapest price for batching it in for you, right? That's their service they're providing. It's permissionless. You don't have to use them. You can always go direct to Celestia. The same for like prover networks. The provers are all sort of like competing each other for like who can do the proof for the cheapest. The one that does and gets in is the one that gets the reward for it. So like now you're creating like just like in simple economic terms like open markets that people can like compete about it rather than having like a decentralized system. And the only like security that you really are there dependent on is the DA layer.
So I guess I'm not 100% convinced that you're not going to have MEV in the system because.
Oh, you are. At
Yeah.
the moment. Yeah, you totally are.
The batch rather than the sequence of ordering the executing the transactions themselves and ordering.
Yeah, so this first part we're talking about security from like I guess like a censorship perspective, right?
Yeah.
Then there is a security from like well, who's going to be trying, like who extracts the value, who gets rewards. And we kind of want to build systems where the app at least gets to choose this. Whether the app wants to choose batches to get rewards in the way that they order the transactions, batches maybe similar to builders in the PVS sense, or whether they want to give it to provers in some way. Like we want to make sure at least that the application has some control with that. And I think a lot of this comes down to how that fork choice rule works. So when you're submitting the transactions on the DA layer, the order with which the transactions are on the DA layer does not have to be the order with which you execute across. So the application itself can define some way so that even if you have a batcher which is trying to like sandwich or do something that like the protocol or the application doesn't want, the application can come up with some deterministic way with which it doesn't actually execute it in that same order.
I think this is a great time to go into that. So we kind of glossed over this execution portion, but this execution portion includes this fork choice rule and some of these things. So I think that was a great point on, we can start with enshrined PBS. So, or not enshrined, sorry. We can start with how PBS works, and we can show you that even without having order agnostic applications, you can still have very ordered applications like what we're used to now, like on Ethereum with
Maybe
EVM.
we should just like explain this. So there's like,
Oh.
we kind of talked about two different categories of applications. Order agnostic are like splitwise, where there's not someone who can really extract value. It's just like, okay, you have a debt to me, you have a debt to me, blah, blah, blah. It's like Ticketmaster, like a decentralized Ticketmaster.
Well,
the
you
control,
can abstract a lot of value.
the control of order flow is not something where the person who has control of that can extract some sort of value. Shaking his head.
No, there definitely is ways to extract value.
Isn't the whole point of Ticketmaster that someone can come in, buy all the tickets, and then they have monopoly on actually selling tickets on the secondary market? So there is value in censoring.
That's exactly.
different. Yeah,
So
okay, I see what you mean.
There's in all of these systems, there's always ways to capture value.
And
So
splitwise?
yes, because if there's with splitwise, maybe not, because it's predefined. Like I have some number of people, I divide the cost across 4 or something. But with something that's like with Cycles Money or with Anoma, where I'm trying to find loops, I can totally insert myself in those loops to connect the dots, and I take all of the excess that people incent. Because with MEV, most of the time it is like, I think other people said this is not me, but most of the time in these systems, like we define things like slippage, or we define things like this maximum cost I'm willing to pay.
Mm-hmm.
But with MEV, I can make you pay that maximum cost. I can make you pay the maximum slippage, and that's where the MEV is.
Yeah.
Yeah, so we want systems, ideally, it would be nice if I could just say maximum cost, and most of the time it never gets hit. Yeah, so anyway, we have these order agnostic applications, and we have these ordered applications. And these systems can actually handle both. Ordered applications now rely on something that's like PBS, so proposer builder separation. So I'm going to cover that really, not use a red. I'll use blue to cover PBS really quickly, and then I'll show us how if we have a censorship resistant sequencing layer and base rollups, we can enshrine that in protocol, and we can control where the value goes. So here we have proposer builder separation. It normally works by, we have a proposer here. So the proposer, in this sense, the traditional name for the proposer, even though I disagree with the naming, is the person who's choosing the next block of the L1. So we have this block of the L1. We're going past here. This proposer is choosing this one. They have a monopoly on this at the moment. they choose the proposer, and now we have our builders. Our builders over here. They're the ones who are getting really clever with transactions. We're going to have transaction 3, 2, 2, 1. And we're going to, instead of ordering here, we're going to order them as 3, 2, 1, because that gives this builder a better chance to capture MEV. So you have many of these builders. They're organizing these transactions. They're actually building the block. They're executing these transactions. They're finding the way that they can capture the most value. And then now they're all competing to actually get this slot. And this is what proposer-builder separation, how it works, is that you have some centralized relay at the moment, like flashbots, or this something to do with that. And these builders submit bids. They say, I want, given a set of transactions, I will pay this much. And these bids are these tips. And the proposer doesn't even have to touch transactions yet. They don't even have to run a mempool at the moment. All they do is they wait there. They wait for their turn. The builders will submit a bid. They submit a bid. The proposer says, OK, I'm just going to take the highest bid. I haven't seen the transactions yet. The transactions are still private. I haven't seen them. I'm going to sign this block, though, because you gave me the highest bid. So I'm going to sign it, sign this proposal. And then after I give you the signature, now here's the thing. I can't equivocate. I can't sign two things. I can only sign one thing. So it works out. Because now the builder says, OK, now I have your signature. I know that this is going to be the next block because you're the proposer. And guess what? Now I'm going to gossip these transactions that previously were private. Those are my own order flow and my own thing. And now this is where the things that we were talking about before, where who captures the value here? The proposer does. Because the builders that are organizing these blocks are being really competitive, but they're submitting bids to the proposer. And because they have to be so competitive, the proposer is the one they still capture some value, but they don't capture nearly the amount that the proposers do. So we don't like that the proposer's capturing value here. So we can improve upon the system in a way that I think is kind of neat.
But this is for a consensus kind of chain. You're transferring this to a rollup where you don't actually have a proposer.
The proposer here, you do have a proposer technically because the L1 proposer is always your proposer, even for a rollup. So what we want to do is we have to fix this, it requires one thing, and it requires that instead of having one proposer, like what Callum is saying, I have many proposers. Or you have to have some mechanism of censorship resistance. So you have to have a mechanism on the sequencing layer. Wherever your sequencing layer is, you have to have some mechanism where this is no longer a single proposer, it's multiple proposers. So let's make the assumption of censorship resistance. We have to make the assumption of censorship resistant blocks. Each block is censorship resistant. Now, this can be a little bit confusing because traditionally when we talk about censorship resistance, we're like, oh, you could be censored for one block, it's okay, just get it in on the next block. But no, that's not good enough here. We need censorship resistance per each block in order for this to work. So this is where you have multiple proposers. Instead of one proposer dictating, having a monopoly over everything that goes in that block, we're going to have many proposers include. So now proposers are, and you have no benefit of, you don't get the decision of what goes in. So because of that, now we have our same system that we have here. We have builders. We have builders building these roll-up blocks like they did before. They come up with the best version that makes them the most money. And then they bid. They're still bidding. But here's the thing. Where does the money go from the bid? That's where the application comes in. The application can choose that now because of the censorship-resistant block. So it's still the exact same system that we had before, except for the money's not going to the proposer. The money's going wherever we want to in a programmatic way.
Do you want to go through that flow?
Yeah, we can. It's the same flow as before, where we have these L1 blocks. But now I'm going to say that, let's say we have three proposers here: P1, P2, P3, and we're going to do that again. And so this right here, and this entire set of 3 different L1 proposers, they're the ones who are building this next block. But they all 3 would have to, let's just say that for now, for simplicity's sake, they all 3 would have to collude to censor a builder. So now we have the competitive builder, but the builder in their bid, they're not giving the money to the proposer. It's not a tip. It still is a bid. The money's going somewhere, but that's dependent upon the application, because now the builder transactions, they build a header, and in it, normally it has a tip, and this tip would normally go to the proposer. But now our fork choice rule for a based rollup, so in our DA block, we have a bunch of, so in this block, so I'm taking like a subset of this block, there's 3 sections here that are contributions from the proposers. Now I'm going to have, let's say we have 2 builders, builder A, BA, and BB. And so this is a rollup block from BA, and this is a rollup block from builder B. This rollup had a tip to the application, not to the proposer, of 10, and this one had a tip of 9. So guess what our fork choice rule is? Our fork choice rule is whoever pays us the most. So now that value, all the money that comes from the excess, so like in these restrictions for users, it's like I specify the max that I'm willing to pay. All that excess, we have control over now. So there's still better things that you can do, but I'll get to that in a second. At the moment, you can take the existing system that works now. If you have censorship-resistant blocks, you can have these based rollups that use these fork choice rules and the proposers of the L1 to have really good sequencing. They inherit the sequencing of the L1. They inherit the DA, the publishing, all the other security elements they're inheriting from the L1. They're using their fork choice rule, though, to capture their own value because we have censorship-resistant blocks. So that's already like the first system, but there's actually cooler systems. Yep.
So what exactly does censorship-resistant blocks mean here? Because you said something about it's not even okay to be censored for one block. So what exactly do you do for this to work?
So normally, if we only had one proposer, so this is like the status quo. This is what happens on Ethereum now. There's a single proposer. They have a monopoly, so they're going to pick the one with a tip that goes to them. Where if there's multiple proposers here, we have to collude in order to pay the tip to us, instead of the tip going to wherever the fork choice rule is. So the problem is that you can still have, let's not call it a tip, let's call it a, I don't know. This is a roll-up tip, and this is a proposer tip. You can still have both of these things in both systems. It's just the fact that you can't exploit it. So with the proposer tip, they're going to pick the P tip that's best for them. And the roll-up tip now, they simply, even though this roll-up block is worse, it's tipped worse, but they're not going to pick this one. They're just going to completely leave it out of the block. And then you need censorship resistance per block because, well, oh, but I can include this block later, maybe, but it might be too late.
So the assumption is that there is like one honest proposer that will take the block that has the highest roll-up tip, and he's not going to care about that. You might try to bribe people, but you assume that one of the proposers will have that block.
You have to collude in order to have that monopoly.
So it's enough to have one honest proposer that like does the right.
It's a little bit more complex with there. It's like 1/3 of the voting power is still. You can always censor if you have 1/3, but now you can also force inclusion if you have 1/3.
But if there's multiple proposers in one block, aren't all the proposers going to choose the block that's built with them with the highest tip to them? So they would all have the same one?
They can still definitely pick the transactions that are tipping them the best, but you're also incentivized to pick like the transactions that...
Because the application needs to see the one that's best for the roll-up,
yeah.
but not best for them. But if it's always... If the roll-ups are going to be, if the proposers are always greedy, even if there's like 10 of them, they're all going to pick the same block, right? They have one that has the highest proposer tip.
But not, let's say that in 10 here, the 10, not a single one of them, of the 10 that actually get included in the signatures of the block, that not all 10 of them can't include even one of these.
So you are making an assumption that there are some people that are
There's still-
altruistic in a sense, right? Because they might-
Not altruistic. It's yeah, honest.
Yeah, honest. Yeah.
You have to assume that there's at least 1/3 of the validators, 1/3 of the voting power that's not censoring,
Makes sense.
in order to have censorship-resistant blocks.
Okay.
Yeah.
Thanks.
Does that make sense?
You have some here where you decide which transaction are going to be included before we know the content of this transaction. So that way, like I can buy, let's say, a transaction swap in the next block that get put on chain, and then once this cannot be reverted, it's finalized. I actually close the content of my transaction, so now the builder cannot even reorder it because we already know the order.
I think I get it. I'm not sure, but we are going to cover order agnostic where we switch this up.
Okay.
You don't have to use this. I actually think this is way more boring. Yeah?
Very stupid, naive question, but like for me, like intuitively, it feels almost backwards in the sense that like on Ethereum, the main problems are builder censorship and like private overflow to builders. How does this kind of change that dynamic?
Builder censorship. So yeah, this solves the, so the censorship resistance here is key for solving builder censorship.
The censorship resistance comes from where here, exactly?
Isn't the fact that there's multiple builders competing against
Multiple,
each other that stops the resistance?
the censorship comes from multiple proposers for each block.
Right, but if you have a situation where like you have a power law with the builders, right, same as Ethereum, and you have like most blocks being created by a couple of builders that then have like private order flow, like does it, like how does having multiple proposers help you?
Multiple proposers helps because if we, now you can include, like in here for the rollup, I can include headers that are built by these, let's say even if we only have 3 headers, 3 builders, I can include the headers from all 3. And then I use a fork choice rule. So I'm taking what exists on Ethereum now and I'm putting it in protocol.
Got it. So each proposer can pick a different header, essentially.
Yeah. It's yeah, exactly.
You should also consider like there are multiple ways of making censorship-resistant blocks, and multiple proposals just like one of the ways to achieve that.
I'm just trying to see the link.
Yeah. So
Couldn't you just have a single proposer and just that proposer includes all bids? And
what's
then
forcing them to include all bids?
they get the most money.
I think they would. Does that make the assumption that the tip here is smaller than the combined tips, or what do you?
Because my initial thing is like, okay, so every single proposer, no matter how many proposers you have, will always choose the block that's built with them with the highest tip to them. So
Yeah.
in a homogeneous like a network, if everyone receives the same blocks, they're all going to pick the same one, right?
As long as they include, more than one. Yeah. So like
what's
they
to
have
stop,
to.
in this case, what's to stop all proposers concluding BB?
Well, there's nothing stopping from more than like 1/3 from censoring ever. So if you have 1/3,
it's not
you
about
can.
censoring. It's just like that's the one that's the greediest algorithm.
Well, if you don't censor, now you have 2. If you do censor, you have 1, and now you can't use a fork choice rule.
So you want to incentivize the proposer to include both bits.
Yeah.
Of the,
So if they include multiple transactions here, now this tip still exists. It's just not the majority of the MEV. It's a very small portion, and now all these proposers who included transactions here, they share these tips presumably.
okay.
but-
so they want to get as many of them as possible. They want
Yeah.
the tip from BA.
If anyone's willing to
BB,
submit a rollup block, it's advantageous for the proposers to include it because they get those fees.
and then that header goes into a Celestia or like a DA block,
Mm-hmm.
and then in the following block, the builder then submits the transactions that
Yeah,
follow,
exactly.
right? And so all builders can see the transactions that are being committed by the DA layer. So they'll see that which one won, which one had the highest roll-up tip,
Mm-hmm. Yeah.
and so then they'll know not to submit their transaction, right?
Yeah. There's probably some games in there. You might need some proving systems. I'm going to wave my hands. Okay. Do we have any more questions before we move on? Yeah?
Do people understand that? I was just
Okay.
learning that as well.
Okay. So,
He's got his hand raised.
And I'm just, where are you generating the proofs here and in the collecting the transactions and then like the execution afterwards as well?
the proof, there's a sort of wide design space. As a prover, as a builder, it's if you had fast enough proving. I could just include the proof with my header. We don't have that yet, though, so yeah.
Well, it matters how many transactions, but yeah.
Good point. Yeah?
So this assumes that the proposer tips are part of the blocks, right? Because the proposers get the tip if this block is included. Then, or yeah. So what stops me from setting up a system where I'm like, I will pay you a tip, but only if my block actually is the fork choice that wins. So you do the tip out of band. You're like, if you include something that will make my block not the block, I will not pay you.
But you have to bribe all the proposers to not include the competitive block.
Yeah, I know.
Which eventually there is probably some price.
Yeah, right.
And then the idea is that hopefully that price isn't sufficient enough
Yeah.
to encourage that.
Yeah.
But there's the price of censorship, right?
Yeah.
Like how much.
I'm just trying to
Always thinking about out-of-band payments is always important. Yeah.
Yeah, I'm just trying to understand, because this seems like you're just sort of trying to make the bribe, let's call it, part of the system. But
Oh,
what if we just
100%.
go out of it again? Like,
That is
what if we
exactly
just-
what we're doing.
Right, but what if we just take it out of the system again and just
Yeah,
do it
yeah.
We can always do that.
Yeah. Still there, you need the ability to censor. So you still have to convince the validators in either way to
Right.
censor in order for this not to work.
Right.
Yeah. So as long as you don't have that ability, which is, I don't know which chains actually have that right now. But you can do it in multiple ways. You don't need multiple proposers. You can use, like Cosmos right now has vote extensions. You can use vote extensions, right? People do that right now. They sell the top of the block. Yeah. Yeah. Okay, so we don't have much time on. I want to cover the cool thing more. This is the boring thing. This is good because we can still capture value, but it's also still really lame because it's not the value is going to the application, and maybe we want the value to go to the user, and that might be a bit more complex. And we have more tools there, though. We have more tools if we use something that is more order agnostic. So the order agnostic way of doing this is you actually post your transactions first. So instead of having a builder here that has this private order flow that I get things, we're going to do the original thing that Callum was talking about. We're going to take our transactions. We're going to submit them directly to the DA layer or sequencing layer, however you want to call it. So now we have these two transactions here. And now these two transactions are timestamped, they're published, and they must be included in the next block in some way. That doesn't mean that they get executed. It just means that they're part of protocol now. Right? So now I have these two transactions here. We're going to go to our execution. And we are going to, in this order agnostic way, I can have, well, actually, I take it back. It doesn't have to be order agnostic. Huh. The ordering of these transactions doesn't necessarily have to be order agnostic, but you can publish things first. And now I can have headers. I can have a block builder submit headers, so we still have the same form before. So we publish all the transactions, and now we have builders. They're going to build these blocks. So I'm going to these roll-up blocks.
Your squares are getting worse.
That one's a house, that one's a square. So we're going to take these transactions that are directly submitted first, and then now these builders, they have to build the block in the way that fulfills some optimization function in the best way. So whatever that is, now here I think you can get a lot more creative than just using like the traditional prover builder separation and sticking it in protocol. Sure, you can do that. It's a little bit boring. This is more fun.
So what you're just saying, to like repeat the point here, is the proposer, like the DA proposer, no matter which way they order the transactions, that can be overridden by how the builder proposes how those transactions should be ordered.
Exactly.
Right?
Yeah.
So it's even if you can't bribe the proposer of Celestia or any other DA layer, because that isn't actually what might be the way that's executed.
That's why I like to say timestamped, because it's the same thing as saying ordered, but it's saying that like these transactions have a timestamp if you need it, but in reality it's more just inclusion. So these transactions get included. These builders, they're going to build headers that fulfill some function. With AMMs, like a fun one is like you use some convex function to optimize the AMM. Let's say you want to optimize for LPs. I want my block, whoever can organize these transactions in the best way to give LPs the most money, And let's say this person does it. Now this is the block. That's the canonical block for the rollup, and the rollup will just we build on that block. And I think that's like this way of first posting transactions and then getting clever with how you actually order them, or even ordering them deterministically in some cases, is way more fun.
In that case, would they also do the execution and the proof of execution if the data is already done?
Yeah, you could do it here. Oh, and the fun thing here is why I think this is more fun is because if we go back to that liquidation example, when you have proof or builder separation, you're extracting the maximum amount that you can, and at least it's not going to the proposer now, but it's still abstracted, and now you have to find a way to give that back to users. And most of the times, like, token holders and users are not the same thing. And screw token holders anyway. Yes, thank you. And so we don't really care about token holders. We care about users. So in the case of having an order agnostic in here, you can have an order agnostic application when the order doesn't actually matter. The application, instead of picking, it holds the auction in protocol. Still, so we're still holding these auctions in protocol, but now the auction is directly based on the transaction that refunds the user the most. That's the transaction that we pick, because that's what we care about. There, MEV solved. It's that simple.
Are there any disadvantages of this approach?
No disadvantage. No, just kidding.
Because you lose something because transactions are private before they're executed. I assume you might
Typically.
lose MEV to
Yeah.
faster chains in a sense, right? They might see a transaction that were posted to you, and then they might do something based on that.
There could be something there. Yeah. I guarantee that there are. I don't know them. Yeah.
They'll figure it out.
Yeah. So that's for someone else. No, I'm kidding. But like sometimes there's just so many different possibilities that can occur that like I think you just have to get the system live, and like we're just gonna have to like it's gonna be a few years. We're gonna demo it. We're gonna see that like actually, totally is bonked. This doesn't work, or something like that. And we just have to figure it out. Anyway, I think we're out of time.
Okay. Yeah, I think we have a 10-minute break, right, before the next people come on.